t smaller, v dl is equal to 0. And it is equal to 0 just because the motion is potential. If we take the boundary as a circle, we can write down that v r1 times 2 pi r1 is equal to 1 r2 times 2 pi r2, which then leads us to the conclusion that Vr is proportional to 1 over r. So, what's the message? The message is that although motion is potential, not only trivial solution, namely v equal to 0, are possible, but also solution singular at the origin has some room to exist, and we call such solution for the velocities singular at the origin as a vortex. And let's discuss. You see, now from the fact that the wave function casts this form and in the fact that our motion is potential, we conclude that non-trivial solution, namely 1 over r, are possible. What does it mean? Let's discuss the circulation quantization and derive this result more rigorously. Okay? Let's write a gradient in polar coordinate system. Polar coordinate system means x is equal to r cosine phi, y is equal to r sinus phi, then tangent phi is equal to y over x, and r is equal to square root of x squared plus y. This is our polar coordinate system. So, the gradient, the nabla operator, is written as LR d over dr in polar coordinate system plus E phi 1 over r d over d phi plus Lz d over dz. So what we assume that we have a cylinder, and this is z-axis. So we study quantization in the plane, and nothing depends on z-axis. So if we assume that our phase of the wave function is proportional to the phase of polar coordinate system, let's assume that chi is equal to alpha phi, where we identify alpha later, and if we calculate the gradient of phi, you see that chi doesn't depend on r, it doesn't depend on z, it only depends on phi. Then this is alpha over r E phi. You see that the hint that we should have this solution actually translated to the statement that your phase is just proportional to the polar angle. What is alpha? If we rotate our system to the angle 2 pi, S where S is integer number, then the wave function remains the same. Psi prime is equal to psi. So then we can conclude that alpha is equal to S, where S is 1, 2, 3, 4, and so on and so forth, is integer number, or so-called binding number. Okay, let's come back and calculate the circulation, as I said, gamma naught, which is integral over circle v dl. So it's 2 pi you remember that ds of v, it's h over m gradient chi, so this is h over m s over r. So this is 2 pi h over m s, and that's it. So this is a circulation. So I should multiply it by 2 pi r, and if I multiply it by 2 pi r is cancelled, so I have this one. If s takes the minimal value, and minimal value is 1, then we have a quantum of circulation. If s equal to 1, we have a gamma naught. Let's understand how big the value gamma naught is. Let's plug in the constants. So gamma naught, first h bar times 2 pi is h without bar, it's 6 to the power, 6 times 10 to the minus 27. If I put the helium mass, helium-4, it's 4 times 1.6 times 10 to the minus 24. So in total, we have 10 to the minus 3 centimeters squared over second. So this is a quantum of circulation. And this circulation is associated with vortices. So what we have found is a solution which has a core, the line where your velocity field is singular, and this is the vortex. Let's calculate the momentum of the vortex and energy of the vortex in order to see what happens with the vortices when you create them in the system. And in order to create vortex, one just needs to rotate system. Suppose you have a cylinder, you have a glass with your liquid helium in superfluid phase, you start to rotate them. And rotating this superfluid substance with some velocity will eventually lead to creation of first vortex. If you rotate it more and more, there will be more vortices, and if you rotate it more and more, eventually all vortices will melt together and superfluid substance will be destroyed. So the creation of vortices is a mechanism of destruction of your superfluid substance when you start to rotate it in the reservoir. Okay, the momentum of the vortex is equal to You take a cylinder or reservoir of the height L, so it's L times integral from 0 to R node, and R node is a diameter of reservoir. Here we have R dr, which comes from the Jacobian in a cylindrical system. Nothing depends on pi. We have 2 pi, and here we have to write something like R times P. This is inertia momentum, and we study projection on the z-axis. So this is R times density, since we have some density of superfluid substance, times VR, where VR is velocity field, which we just discussed. Okay, V is precisely this, E. So the density is constant. Let's plug in everything. Rho times L times 2 pi. Here it's integral from 0 to R node. R square, we have H over M times S over R dr. So we have 1/2 R node square. So it's a pi rho L R node square times H over M S. So this is volume, and rho times volume is the mass of liquid. Mass of liquid divided by mass of single particle in the liquid is the number of particles. So this is M times H times S. So you see that each vortex brings S to the total inertia moment. If we calculate the energy the same way, this is L times integral to rho node. Here we have R dr 2 pi, and here we should write down rho v squared over half. This is energy of the vortex. And I deliberately didn't put anything here. Let's see. For the first integral, it was quite clear that it doesn't diverge, so we were fine to put here 0. So it's 2 pi L rho H squared over M squared S squared. Here integral R node R dr times R squared. Oh, sorry. Times 1 over R squared. So you see that the integral behaves as dr over R. Therefore, it is logarithmically divergent. Therefore, in order to cut this integral in the lower limit, we need to put interatomic distance, which is a natural cut of all divergences in solid state. So there is no divergences on small distances, because everything should be regularized by interatomic distance. So what we have here is 2 pi L rho H squared over M squared S squared times logarithm R node over M. So to create the vortex costs energy, and this is so-called vortex logarithm. So what we see from this simple exercise. So let's look at the reservoir from the top. So we create a vortex in the system by rotating it. And the momentum of the vortex is proportional to winding number S, while the energy of the vortex is proportional to the number of S squared. So since energy grows as a square, it's not energetically favorable to create vortices with a winding number bigger than 1, because it costs a square energy. While if we create two vortices with S equal to 1, it costs less energy. 2 squared is 4, while 1 plus 1 is equal to 2. So it's twice costly to have vortex with a higher winding number than to have two of them with a smaller winding number. Then, if we have two vortices, they cannot merge, because merging of them costs also energy. They can join to single one, because then you lose this and you lose the energy. Since they cannot join, and you see the direction of your vorticity is opposite, let me plot it here in zoomed way. So if it goes this way, here it goes other way. And like in classical electrodynamics, you see that these vortices will repel each other. This is also the reason why they cannot merge. So you see how many conclusions we have drawn from simple consideration of this vortices. So then,
I don't know why they repel here.
Because they move in the opposite direction. Look, it's like create two currents, two wires, and then you see that the forces between two currents running in opposite direction will repel them each. And to do it, you know that the circulation, if I create now a lot of vortices, and all of them will have the same circulation, you know, because it is related to rotation of the reservoir. The circulations within the reservoir cancel each other. So here we have cancellation, and only on the boundary we have something. Only here we have a summation of all circulations, and then in this envelope they will come to the boundary. All the rest inside is cancelled. Okay, then let's take this reservoir and rotate it with angular velocity omega. If you repeat the arguments of Landau for criterion, we can write down that the energy in rotating frame is normal inertial. The first Landau criterion was related to the Galilean invariancy of your system. So we had the flow running with a constant velocity, and then we come from the moving frame to laboratory frame. But both coordinate systems were inertial. Here we are talking about non-inertial coordinate system, because we're coming out from the rotating frame to the laboratory frame. So the energy is equal to E minus m omega, where m this inertial momentum, so omega is directed along z direction, and m has also z direction. So this is E minus mz omega, and therefore in order to have E prime negative, the same way as Landau criterion, we have omega bigger than omega c equal to E over m. So, if we now rotate our container with an angular velocity omega much larger than omega c, let's see what happens. Let's see how many vortices you create in the system. Namely, look, you first start to rotate your container. If you rotate it with a velocity sufficient to create one vortex, you do it. If you rotate it with a high velocity, you then create two vortices. Why two? Because to create two is less energetically costly than to create one. Then you rotate it further. You create third vortex, fourth, fifth, and so on and so forth. It's like quantization. Since the circulation is quantized, here you also have quantized structure of vortices which you create more and more in the system. But if your angular velocity is very large, let's estimate how many vortices you can create. So, since V is R times omega, we calculate the circulation over dl and write down that this is m times the circulation quantum. You create n vortices. Each of them carries Weidlich number n equal to 1. So the left hand side is equal to omega s, and this is n vort times gamma node. So your number of vortices is equal to 2 omega s divided by circulation quantum. Okay, so being back to Landau assumption about the spectrum, you see that this spectrum actually takes both features of a superfluid substance. First of all, it has phonon branch of the spectrum, which can be derived microscopically, for example, for the model of weakly interacting bosons. But then, if your energy exceeds some gap value, you start to create vortices in the system. And this is how you destroy your superfluidity. So then, as I said, one feature is phonons, and another one is rotons. An existence of these vortices has also been seen in the experiment with rotating superfluid substances. So then you see that the structure of the spectrum is actually justified, and this spectrum suits very well for the purposes of two-fluid model of the superfluidity. So, summarizing, what do we have? We have the experimental observation that in helium, below some critical temperature, systems start to behave quite unusually. Namely, it demonstrates losing of friction, or particle losing of friction on one hand, and infinite thermoconductivity on the other hand. Thermoconductivity means also mass transfer without friction. How can it happen? It is explained through the assumption that below this temperature, your helium actually consists of two liquids. One liquid is normal one component is normal one, which is like in all usual substances. It is responsible for friction, it is responsible for any kind of normal behavior. However, there is another one component, which is superfluid one, which is responsible for all unusual behavior. But since the number of mass, the amount of mass is concerned, therefore these two densities should satisfy the condition that the sum of normal and superfluid density is a constant. If you lower down the temperature, you will have more superfluid component and less normal. If you go up to the temperature, you have other way around, more normal component and less superfluid. If you exceed the temperature of superfluid transition, then all component is normal and the system behaves as a normal one. For superfluid component, we need to say that first, it's a system which is in the condensation regime. So we are below Bose-condensation transition, and moreover, this is interacting system. Namely, the long wave behavior of this system is characterized by the phonon-like dispersion, which then tells us that if your fluid runs through the capillary with a velocity smaller than the sound velocity in the system, then it remains superfluid and it creates no friction, because if the velocity is smaller than the phonon velocity, there is no way to emit or absorb phonon to the walls of the capillary. If, however, a system runs faster than the sound velocity, then you have mechanism of dissipation of energy through the system through the emission and absorption of phonons from the capillary. This dissipation of energy can be understood as a friction. Then, in a superfluid state, we see that we can characterize this superfluid state by a single wave function with a modulus and phase. And the phase of the system is such that it quantizes the circulation. Namely, the fields of velocity has a singularity at r equal to 0. At r equal to 0, you have the normal component. By the way, when I'm talking r equal to 0, it's a local coordinate system of each vortex. It's not a global one of the system. But of course, if you create vortices in the system, from symmetry point of view, it's quite natural that you create first one in the center of the rotating container. So you see that this kind of behavior, singular behavior of the superfluid velocity tells you that if you rotate your container, you can create this kind of defects or vortices in the system, and more you rotate your container, more defects are in the system, and then if at the end of the day you rotate it so quick that you destroy superfluidity in the system completely. So superfluidity is coherent phenomenon. It's associated with behavior of the phase. You will see that in superconductivity, this is the same way. You can put a gradient of the phase or gradient to electric field to the system, and then there will be current running through the system without energy, without no energy losses, namely without friction, and this is nothing but superconductivity. Possibility to conduct electric current without energy losses is nothing but that, and this is closely related to phenomenon of superfluidity, and Professor Yevtushenko will tell you that in some sense superconductivity is a superfluidity of Cooper pairs. That's all for today. Any questions? So tomorrow we meet at the same time, right? Yeah, still, yeah. And tomorrow we continue with magnetism.
It is
Okay,
you said that the wiring, the electrical wiring is like, I don't know how to explain it. Wiring small text.
like, you know what vortex is? You know what Whirlpool is? So you have a liquid running this way.
And the Georgian physicist.
You can see, say, two currents running here and there. And if you do it, say, in electrodynamics, just run two currents. Just on the boundary. Suppose that you have some current running on the boundary. You don't care what happens inside the vortex. Just you rotate some substance. You have a Whirlpool, kind of. I don't know how to, but they can not attract each other. Because if they attract each other, then there will be attempts to melt and to form a vortex of bigger size. And this is impossible. You see, from the energy arguments, you cannot get it.
Can I use this?
One vortex from two.
I don't know this last time
Look, this is like line. You have a line of normal components where the superfluidity is destroyed. So along this line, the component is normal. Out of this line is superfluid, and this is called vortex. So when you rotate your cylinder, you first destroy superfluidity on the axis. Then you create kind of lattice of the lines where superfluidity is destroyed. And then you destroy it completely. And these lines are nothing but this local destruction of superfluidity and vortex. This line is this singularity that we are Vs is H over N S over R.
So maybe if we have actually documented then when we set the system,
You lump some energy, right? And pumping some energy. If you exceed some threshold, this one, which is delta. If you pump more than the delta energy, then this energy is sufficient to be absorbed in the creation of the first vortex. So then the system minimizes itself such a way it cannot dissipate energy because it's superfluid. Then, in order to accumulate this energy which you try to pump in the system, it creates one vortex. Namely, the superfluidity is destroyed along one line. When you rotate it with higher velocity, then you create second vortex because the circulation is quantized, and so on and so forth. If you rotate quick enough, you create many vortexes. And eventually, they all destroy the superconducting, the superfluid. Yeah.
There is some confusing
Yeah, suppose you have the container with superfluid liquid, and you start to rotate. The superfluid, you are sufficient to low temperature. Everything is superfluid. Everything is superfluid, so you are sitting in this. This is normal. This is rho S, and you are here. Everything is superfluid. But then you start to rotate, namely, you put some energy into the system. And if energy is larger than this gap associated with the creation of single vortex, then you create one. And this is how much energy it costs you. But this is the same like in Landau criterion. When you start to run it through the capillary, and if the velocity is higher than something, then it starts to dissipate. So if you take a superfluid liquid and push it through the capillary with high enough velocity, it destructs superfluidity. It destroys superfluidity. The same way here. If you do it in a container and you start to rotate it, if you rotate it sufficiently quick, you start to destroy superfluidity. And this explains how. And it tells us that destruction of superfluidity occurs through the creation of vortices. Welcome.